sequences. Okay, this is a real important thing to know how to do. And you're looking for patterns basically on this. So this is a sequence. Remember, a sequence is nothing more than a list of numbers that are following some sort of a pattern. It's an infinite set of numbers. So let's put the next terms in the sequence. So it's actually pretty easy. This one's going 1, -2, 3, -4, 5. So the signs are alternating. We call this an alternating sequence. So your next terms after this would be, I'm just going to write down this thing here real quick, and then let's write down the next terms in the sequence. So after that, you would have a -6, then you would have a 7 like that. So it's alternating in sign. So what the thing that we want to try to do is try to do what we call a recurrence relation and then an explicit formula. So we want to be able to see what the pattern is and then try to write that in a formula now. Okay, anytime that you do a recursive relation, you always start this way. You tell me what the first term is. We use A sub n typically for the terminology for a sequence. So that's going to be 1. That's the first term. Okay. Now what we want to do is we want to kind of look at a pattern on this for a minute. So I'm going to write down the next couple of terms in the sequence and kind of show you what I see happening. Well, one thing that I see on the next term is there's a -1 there. It's multiplying by something. And then it's taking this previous term, and of course it's adding 1 to it. Okay, you can tell it's going up by 1. And then when you go to this next thing, what it's doing is now you're going to have a +1 times something. Then you're going to take the previous term, but you're going to look at the positive of that. So I'm going to write an absolute value in there, kind of like that. Okay, because you're not doing -2 plus 1, you're doing 2 plus 1, right? Okay, and then if we go to this next thing, we're back to a -1 times. Then we would take the previous term. I'm going to put that in absolute value again, and then +1 like that. So what I'm trying to do is kind of give you a pattern that's going through on this then. So let's kind of see if we're on the right track here, all right? Okay, so let's see if that works now. Remember what we're doing is always the previous term +1, but then we either multiplying it by -1 or 1. Is everybody with me on that? Okay. So we're going to try to write, when we do this recurrence relationship, A sub n, what it's doing is it's giving the next term. It's not a formula for the whole sequence, it's for the next term. So here's kind of what we have. One thing that's real important on this is anytime you see this alternating signs, and you'll see this as we study this, if the signs alternate, it has something to do with that expression. Okay, so the idea would be like if you had -1 to an odd power, what would you get? -1, right? What if you had -1 to an even power? What would you get? You get 1, right? So it's the power that causes it to alternate. Okay, so notice when we have the second term, when we're on the second term, what's happening is we want that thing right there to be a negative number, like that. Okay, so what we're going to need to have on that is we want to have some sort of an odd power on that like this. So let's kind of try this. Let's look at -1 to the n. Okay, that's going to give you your alternating pattern there. And then what's happening, if you look at this, is we're always doing the absolute value of the previous term and adding 1 to it. Okay, like that. I'm just trying to show you the thought process I think of when I build this together. So what I'm going to do is I'm going to put absolute value of A sub n, like that, and then +1. And then let's see if that's going to generate the next term. Okay, that's the idea. So once you kind of have an idea of how that goes, then you want to make sure that it's right. So if we were to go through and do this now, if we were doing, we have A sub 1 is equal to 1. If we were going to A sub, and this should be an A sub n plus 1 is the way you want to write that. I didn't write that correctly. So that would be A sub n plus 1, because that means that's the next term in the sequence. Okay. So what you would do, if you go on to A2, you're really doing A sub 1 plus 1. Well, let's see if this works or not. Okay, so what we're doing in this particular formula is if we're doing n plus 1, then n is really 1 right now. So if we did that, we'd have negative 1 to the 1. Then we would have the previous term, okay, a sub 1 is equal to 1, plus 1, and let's just see if that does indeed give us a negative 2. What do you think? Looks like it does, right? Okay, because you got negative 1 to the first is negative 1, 1 plus 1 is 2, so that gives negative 2. Now I'm going to do it one more time just to make sure that we're on the right track here, okay? Let's go to A3. If I do A3, what are you doing? You're doing a sub 2 plus 1. So again, you're working with the previous term, and we do this. So according to the formula we built, we have negative 1 to the second. Then we have absolute value of a sub 2. Well, a sub 2 is negative 2. So we have that plus 1. And let's see if that gives us a 3. We're supposed to get a 3 for the third term. Okay, so what's negative 1 to the second? That's positive 1, right? Okay, that would be 3 there. So that appears to be working. Are you convinced that it's working yet? Or do I need to convince you more? Okay, the challenge of that problem is putting that together, is trying to figure out what that pattern is. Sometimes it's very easy, sometimes it's challenging, but one thing that you definitely want to make sure you have down is if you see an alternating sign, then it's going to have something to do with negative 1 to the n. Sometimes it may be negative 1 to the n plus 1, but you kind of play with the pattern until you see how to put that together. So what you're doing in a recurrence relation, you always have to tell me the first term and then what the next term is. That's why we write that as n plus 1. That represents next term. Okay? Does that look reasonable to everybody? Okay. All right. Now what we're going to try to do is we're going to try to do the explicit formula. And remember what your goal on an explicit formula is this. Like if we wanted to find the 1,000th term of this sequence, you wouldn't want to do the recursive relationship because you would have to keep going over and over again until you got to that point. In this particular case, what our goal is to get a formula, we plug 1,000 in and boom, we got the 1,000th term. So what I'm going to do on this is, let's kind of put this together like this now. So I'm going to kind of write out the pattern I see. So if we got a sub 1 is 1. So we know that we have this alternating thing here. Okay, we got that alternating. I'm going to put an n there, but I'm going to erase that in just a minute. And then that's going like that. If we go to a sub 2, again, we have negative 1 to some power, but then we're multiplying by 2. So we know that the number's just going up 1. And if I go a sub 3, I have negative 1 to the n times 3. So I'm trying to just get you a kind of a pattern put together on this. And then we should be able to pretty easily write this. Okay, so one thing that's going on this is, first of all, whatever n is just the number, right? Okay, so that's going 1, 2, 3, 4. All right, now the first one is a positive number, right? Okay, this is a positive number. We got a positive 1 in that first term. So would you like that n to be an even exponent or an odd exponent to make that become positive? Even. So what I'm going to do is I'm going to erase this, and let's change that to an even exponent. And let's just go as small as we can. Let's say that's a second power. Okay, then let's go up from there. Okay, let's go to the next one, and let's say that's a third power, a fourth power, and a fifth power, and so forth like that. And then let's see if we're on the right track with building this thing then, okay? All right, so notice if I do this, if I do a sub 1 now, I've got 1 times 1, or I got 1. So that's the first term in the sequence. Okay, the next one, negative 1 to the third is negative 1, times 2 is negative 2. Next one, that's a positive 1 times 3. So it works, doesn't it? Okay, what I came up with seems to be working. So now all we got to do is formalize this into one simple formula. Okay, so here's what you do. All right, first of all, we know we have negative 1. Okay, but you got to put a expression in terms of n in that exponent. So look at this, real simple. Okay, if you have a sub 1, what's the exponent? 1 more. If you have a sub 2, what's the exponent? 1 more. You guys see what I'm talking about? So you wouldn't put n there. What would you put? n plus 1. Good, because you're going up 1 like that. All right? And see, this thing right here, Now, if you look at this is matching in, right? That's matching in. Okay, so what's going to go there? You're going to multiply by n. There you go. That's it. That's the formula. So you've got the -1 to an n plus 1 power, and then you've just got the n. So what that would be is that would be how you write what we call the explicit formula. Okay? Now you got to play with that a little bit, and one of the things I recommend you do, because sometimes you're going to struggle with doing this a little bit, is just write things down. Okay? The key thing is anytime you have alternating, you want to make sure that you pay attention to that, because that's going to be a part of your formula. Okay, if the signs alternate, and then just look what the pattern is. Okay? To me, if you write things out like this, you'll see the connections a little bit better. What do you think? Okay, does that look all right to everybody? Okay, that was not too bad. The thing on that's a little tricky is that absolute value. You have to have absolute value, otherwise it's going to mess the signs up, because you're always going up 1 in the next term in the sequence, but you're adding 1 to the absolute value of the number. Okay, that's important. Okay, let's take a look at one more like this, and then we're going to transition a little bit into the idea of a limit of a sequence, which is the calculus part of this we start looking at. So let's look at this one. Generally, writing the next terms in a sequence is pretty easy as long as you see the pattern. So here's my first terms in the sequence. Okay. So what are we really doing? What are you doing to get the next number? What's going on? Just taking half of it, right? So you would have half of 4 is 2, half of 2 is 1, half of 1 is a half. Okay, and then you would go to a fourth, and so forth like that. So you're just cutting everything in half when you do that then. Okay, so what we're going to do is we're going to do a recurrence relation, and then we're going to do an explicit formula. Okay, sometimes one way is easier than the other one. Okay, to me the recurrence relation is very simple on this one, but the explicit formula is a little harder. Okay, so again, when you do an explicit or a recurrence relation, the first thing I always do is you tell me what the first term is. That's basic. Okay, you got to do that. Then what you have to do is you have to tell me what the next term in the sequence is, and you always say a sub n plus 1. So we're always going to start with a sub 1 and then go to the next term. Okay, well, what are we doing? What do we do to that 64 to make it turn into a 32? What did we just do? We divided it by 2. So if you look at it, you could kind of think of it like this then. You're going to take a term in the sequence, and then you're going to divide it by 2. Okay? And then once you do that, you want to just verify and make sure that that's a correct recurrence relation. So that appears to be the right answer. Well, let's go to a sub 2. When you do a sub 2, you would really be doing a sub 1 plus 1. And what that's going to tell you to do is to do a of 1 over 2. That's what that tells you to do now. Now notice that in this formula, those are what's matching up. Okay, well, what's that going to be? That's just going to be a sub 1, which is 64, over 2 is going to give you 32. Okay, I just want you to understand how the subscripts work on that, because that's important. I'll do it one more time. A sub 3, what's that? That's a sub 2 plus 1. So that's a sub 2 over 2. Okay, well, what's a sub 2? A sub 2 is 32, and then 32 over 2 is 16, and so forth. Okay, does everybody see how that works? Okay, mostly the subscripts. It's easy to tell that you're dividing by 2 on that. But getting the subscript in the formula, always tell me what a sub 1 is, and then give me a formula for a sub n plus 1. Okay, now when you do the explicit formula on this, what I recommend that you do, this I find very helpful, and I would recommend that you do this when you need to. What I'm going to do is kind of have you draw a little chart on this, and we're going to start with n equals 1. We're going to go to n equals 2, and let's take this out several terms until we begin to see the pattern. So I'm going to take this up at least to this point right here. Okay, and I might carry that out a little bit further. I think I'm going to carry it out to about 8 terms. That's not necessary probably, but I really want you to see what happens when you start getting into the fractions. Okay, so remember, when you're doing an explicit formula, your goal is just to have a sub n equals whatever. One formula, okay, for the whole thing. Okay, so what I'm going to do on this is I'm going to write down what we have. And I'm going to have you write down, the first term looks like it, so I'm going to put the over 1. There's a reason why I'm doing that, 64 over 1. Then let's just put 32 over 1, and like this, and then let's do, the next one is, hold on, I don't want to do it that way, I want to do it this way. I'm getting ahead of myself here a little bit. Let's just write down the terms in the sequence real quick. So let's do that. So let's do like 64, 32, 16, 8, 4, 2, 1, and then all the way up to a half. Okay? Now your goal on this problem is to make one formula for all those numbers. Okay? So the way I look at this is something's going on with these numbers in the numerator, and what they are is they can be thought of as powers. Okay, so if you go here, for instance, just kind of starting here, that would be like 2 to the first would give you that. Okay, this would be like if you're getting a 1 out of that, that's like a 2 to the 0, right? And then this is like a 2 to the negative 1 and so forth like that. But the other thing I see on here is I've got patterns when I'm dividing these things by 2. So I'm going to write this out one more step, and this will kind of help you see this. So I have 64 over 1, then this one is going to be 64 over 2. This one's going to be 64 over 4. This is 64 over 8. That's 64 over 16. And so forth. Okay, so now I'm beginning to see a pattern. 64 over 32, 64 over 64, and then 64 over 128. Okay, now see, I'm just kind of seeing the pattern and how it relates to 64, how it relates to the first term. So if you kind of see that pattern, then it's not too hard to come up with the formula now. Okay, because what's happening is your numerator is fixed at 64. Okay, what's going on your denominator? What do you see there? What pattern do you see there? Those are powers of 2, aren't they? Okay, you got like 2 to the first, 2 to the second, 2 to the third, 2 to the fourth, and so forth, right? So what you really have going on this problem is, for instance, this would be like 64 over 2 to the second. This is 64 over 2 to the third, and so forth. Okay, so once you kind of see that, then it's pretty easy to write that formula. And it keeps working on this. That's 64 over 2 to the 6th, 64 over 2 to the 7th. If you go backwards, that's 64 over 2 to the 1st, and then 64 over 2 to the 0 like that. Okay? So writing things out in kind of an organized way like that often helps you see the pattern and write the formula. And you might not always go about it the right way. So now I'm ready to write my answer. So my answer for this explicit formula is going to be this. We say a sub n, well, what's the same? It's always got a 64 in it. And then what would be the denominator? What would you use? You've got to be careful about this now too. Okay, notice that when n is 1, you have a 0. If n is 2, you have a 1. If n is 3, you have a 2. So what would that be? It would be 2 to what power? It's not 2 to the n now, it's something else. N minus 1, right. See, this exponent is always 1 less than n. So you'd have to say 2 to the n minus 1. Okay, now it works. Okay, it works beautifully. So if you start with n equals 1, then you would have 64 over 2 to the 0 and so forth, like that. So that would be the way that you would write that out, is like that. Okay, does that make sense to everybody? Okay. That's a good way to do that when you don't see the pattern and can't write the formula in your head. Write it out and start looking for patterns. That'll help you. Okay? All right, is there any question on that? I'm not done with the problem. I'm going to go a little bit further with this one, because you could write the answer that way if you wanted to, but you could also work this out. So what I'm going to do also on this is I'm going to go ahead and work this out. So you could write this as 64 is... let's see, that's 2 to the 6th power, I think. Okay, yeah, 2 to the 6th is 64. You could check that on a calculator. Then I'm going to write that as 2 to the n minus 1. Well, what you could do is you could subtract those exponents. Okay, you could simplify that algebraically by just saying this. This is 2 to the 6th minus n minus 1. Okay, you subtract the exponents when you're simplifying because those bases are the same. So you'd have a sub n equals 2 to the 6th minus n plus 1. So you get a sub n is equal to 6 plus 1 is 7 minus n. So that's the way, probably the best way to write the formula is like that. Okay, then it makes it like real easy to get the answer. To me, it's just a simpler form of that. And notice if you did this now, that it would work. So if you had a sub 1, you would have 2 to the 7 minus 1. That's 2 to the 6. So see, that's 64. Okay. If you did a sub 2, you would just do 2 to the 7 minus 2. That's 2 to the 5th. That's equal to 32 and so forth. Okay. I like that formula better, don't you? It's easier. Okay, so you can just algebraically simplify that a little bit to get that then. So one thing that you'll find a lot of times on these problems is they have powers of numbers. Okay, that shows up quite a bit. Okay, all right, so let's move on and let's talk about the limit of a sequence next here and kind of talk a little bit about what that is. I'm going to show you a couple of things on your calculator today too that'll help you process this and everything. So what we do with the limit of a sequence is you can graph a sequence. Now when you graph a sequence, it's not like a curve where it's smooth and connected. It's discrete points, so it's just got points on it. Okay, for instance, if you looked at this particular sequence right here, you want to know what that terminology means first of all, and I just want to go through kind of the arithmetic that I did and how I plotted out that sequence, how I graphed that out. So really I'm just working out the arithmetic. So you're going from 1 to infinity. So I'm starting by plugging in, everywhere I see an n, I plug in a 1, like that. I plug that in like that, then I would work that out. Okay, so I do that. Okay, well that gives you 1 over 2. So negative 1/2 is your first term in the sequence. Just do that in your head. If you go to the second term in the sequence, that goes to 2, that goes to 2. Now you have 1 in the numerator and 5 in the denominator and so forth. Can you guys see that in your head okay? All right. Now, this is an alternating sequence. Now tell me what made this alternating in the formula. That's important. What piece of that? The negative 1 to the n, right? That's important. Okay. When you see that, that's going to tell you that the signs are alternating. Okay. So if you do this, now what I did is I graphed this. You can graph a sequence like this. So instead of having an x-axis, you have an n-axis. And n is whole numbers, 1, 2, 3, 4, and so forth. And then I went ahead and just scaled this because that's really like 0.5. That's like 0.2 and so forth like that. So I just went up to 0.5 and went down to negative 0.5 like that. And I changed them to decimals. So the first term in the sequence is negative 0.5. Then 1/5 is 0.2 and so forth. So if you look at that particular sequence, it's easy to tell what the limit is. It's just the same kind of idea. Now it's alternating, so you're going to notice that it jumps back and forth from above and below the n-axis. But where's it going? Zero, exactly. Okay, so it's the same concept. What you'll find with a sequence is if you can find the limit of the function that's represented by that, it's going to be the same thing. The function would be like if you changed all those n's to x's and graphed that in, like on a graphing calculator, you would end up getting something that kind of had this kind of curve thing like this, alternating up and down like that, and it would still go to 0. Okay, so that's the idea. So first thing we're going to do is visually look at what a limit is before we do this more mechanically, so you can tell on this one that approaches 0. Okay, and that's the idea. Okay, let me open up this app. So is there any question about that? That should be pretty straightforward to start with. Okay, now I'm going to open up this one app on GeoGebra that's kind of another thing that I found that's kind of cool. That shows this. This just shows some examples of some sequences that we're going to learn about. We're going to learn about a geometric sequence, for instance. So a geometric sequence is just like r to the n power. You can change r to whatever number. R is just some positive number. So if you look at that, what does that sequence appear to be approaching? 0, okay? and you have dots on this. One thing on this, you can change the value of R and so forth like that. And the value of R makes a big difference on this one. So if I've got like that, you can tell pretty well that's going to converge to 0. But if I make R big like that, does that thing appear to be converging to any point, or does it just going out of control? So in that case, that would diverge, okay? And there's all kinds of sequence. There's something called a harmonic sequence. If you look at that one, that appears to go to 0 also, doesn't it? Okay? And a lot of times what happens on these problems, if you change this number, sometimes that changes that value like that. This one appears that it might be leveling off at some number. But again, a sequence is just dots. Those are discrete terms, so it's not like a function where it's continuous everywhere. Like that. It's not a continuous function, it's discontinuous. Okay, so that's the idea. So let's go to the next page on the notes here, and let's look at the next kind of key thing I want to look at. I'll get back on here. Okay. And I'm going to show you how to use your calculator on a couple of things. So go ahead and get your calculator out. And we're going to do the problem, because I want you guys to know how to do this. This is different. You may have never learned how to do this before. So I've got most of the stuff written down, but you can write down notes on this. You can also, if you forget how to do this, you can always Google stuff like this and find this. So I'm going to teach you how to graph a sequence. Okay, first thing that you want to do is you want to start by finding your mode button. So you want to press that mode button. You can write any steps down you need to on this. Okay, and what you have is if you go down to this line, right now you're probably on the function mode. Parametric is something we do at the very end of the semester. Polar, if you took trig, you may have learned how to do polar graphs just a little bit. We'll do a little bit at the end of the semester now. Well, you want to go to sequence. So you want to get that highlighted. So just move over to sequence and highlight that. And then that puts you in the sequence mode. Okay? All right? So now what you want to do is we want to go to y equals. And when you do y equals, well, you're just going to put in what I have, but it's going to look like this now. So you're going to have like u of n. That's just the way that's a sequence notation. So what you want to do on this is put in exactly the way I've got it written here. You're doing u sub n equals -1 to the n power divided by, because I'm doing this sequence right here, and then in parentheses, n squared plus 1. So you want to have that in like that. And then you don't really have to put anything for n minimum on this problem. It doesn't make any difference on that. So you just put in u sub n like that. Okay? All right, so that's how you put that in. And then I want to talk about the window a little bit. I can slide that over there if you need to refer to how that's put in your calculator. Okay, now I'm going to go to the window. So the window kind of goes like this, and I'll show you what to set up on this. So when you're doing n minimum, that's going to start at 0, and then we're going to go to like 10. And then this plot start is just making the n's go up by 1. Okay, on a sequence, n is going up by 1. So you want to have that set up like that. You can adjust that and make the sequence go out as far as you want to, but for this problem, 0 to 10 is probably sufficient. Okay, then on the axis, let's see, on the x-axis, we're going 0 to 10, just like this graph is showing. And then for the y's, do your y's like this. Do a y minimum of -0.5 and a y max of 0.5, and then maybe scale that if you want to by 0.1. You can scale by whatever you want to, but that's a logical thing to do, is just go up by 0.1 like that. Okay, and I'll slide that over there if you need to see that then. Okay. Okay, now what you do, if you got everything set up, then you can type graph. Okay, so you got your window, you got your sequence in, and if you've got that all done, now just do graph. And what it'll do is it just puts these dots on here. And there's several things you can do with this. You can still trace and stuff like that. So when you get that in, like if you type trace and you just type n equals 1, for instance, well, the first term of the sequence is -0.5. And if you just after you press trace, if you just press your right arrow key, okay, there's the second term in the sequence. That's 0.2. third, okay? So see, it's alternating back and forth, and you can tell visually that it's going to converge to 0. So it's kind of a nice way to visualize what a sequence looks like. Does that make sense to everybody? Okay? So if you follow that okay, that's something that might come in handy from time to time, is to be able to look at a sequence visually. It helps you see what's going on with that limit. And when we're doing a limit, we're always looking at infinity on a sequence, because that sequence is going out. We're interested if it diverges or converges. Okay, did you guys follow that okay? And that may be something you've never done before, but most graphing calculators are going to do sequences for you, okay? Okay, so let's see. On the next page, what we're going to do here is we're going to do just kind of looking at a graph. Now I'm going to do this one without the calculator. So, and this is just kind of getting you comfortable with this notational system. So you're doing the cosine of n pi from n equals 1 to infinity. Okay, so let's just write out each term. So you're going to do like cosine of 1 pi, then n goes to 2, so you're going to do cosine of 2 pi, cosine of 3 pi, and cosine of 4 pi. So that would represent an explicit formula for that sequence, okay? And then this is a real easy unit circle thing, basically. So if you look at this on a unit circle, if you're doing a cosine, what are you looking at on a cosine on a unit circle? You're looking at the x value, right? So it's going to alternate. If you look at this, it's just basically going to alternate. The cosine of, if you start with 1 pi, okay, the cosine of 1 pi is going to be -1. Cosine of 2 pi is going to be 1. And this is just going to alternate over and over again. So that's going to be -1. Cosine of 2 pi is 1. When you go to 3 pi, just count it out. That's pi, 2 pi, 3 pi, so it goes like that. That's back to -1. And then 4 pi is all the way around the circle twice, so it's 1 like that. Okay? So it kind of goes like this. If you have an odd pi, you're going to be there. If you have an even pi, you're going to have a value of 1. Okay? Sometimes in trig, I'll give a student like a problem like, what's the cosine of 100 pi? Students freak out. Okay? All I'm trying to do is see if you see a pattern. When you have an even pi, what's the cosine? It's 1, right? Okay? That's kind of a pattern to see. Now, if you look at this, if you graph this on the graph, then you would just plot these points like this. So the first term in the sequence is -1, so you just put a dot there. Second term in the sequence is 1. Third term is back to -1. Fourth term's to 1 like that. You don't connect the dots or anything, you just do that, okay? So, do you think that would converge or diverge? Diverge. It doesn't go to the same place, right? That's the thing. It jumps back and forth from 1 to -1, so that's going to diverge. Okay, it's not coming together to some point like that. And it's an alternating sequence, but it's because of the cosine and the fact that the signs are adjusting depending on where you are on the unit circle. That's the idea. Okay, so that's how that goes. That would be one that you could put in your calculator. You would just have to make sure you're in Radian mode, and then you would put that in your calculator if you wanted to. Okay, let's look at this situation here. So let's look at this one. This one is a recursive relation on this one. Okay, so what I've done on this one to begin with, we're going to do the first 4 terms in the sequence. Actually, I gave you this way, so let's go ahead and just write down a sub 0 equals 2/3. So sometimes we start with 0, sometimes we start with 1, and then we're just going to generate these terms. So when we're doing this formula, that's what gives you the next term in the sequence. So if you're going to A1, you're really doing a sub 0 plus 1, so that would be 1 minus a sub 0 over 2, so you're just doing that. Okay, so when I work this out, and you have to work out a bunch of fractions on this problem, so you're doing 1 minus, and I'm going to write this, see if you're dividing by 2, just write that as 1/2 times that 2/3 like that. So this sequence could be thought of as 1 minus 1/2 times a sub n. So it would go like that, okay? Now some of this arithmetic I'm going to do super duper fast, so that's like 1 minus 1/3, so that's 3/3 minus 1/3, so that's 2/3. Okay, so that would be what the next term in the sequence is 2/3, like that, okay? All right, and I'm going to do it a couple of more times, and then you'll see kind of a pattern. Next thing I could do is I go to a sub 1 plus 1, so I can get a sub 2. So according to this formula, I'm doing 1 minus 1/2 of a sub 1. Okay, well, a sub 1 is 1/3, so I'm doing 1 minus 1/2 times, or I'm sorry, 2/3. Now, isn't that the same math problem that I just worked out? Okay, if it's the same math problem, I'm going to hopefully get the same answer. So 1 minus 1/3 is 2/3. So we're getting the same answer. Now, do I need to calculate anything else? It looks like it's just going to keep the same thing over and over again. So sometimes in these sequences, you just get the same answer over and over and over again. Okay, because you're going to be doing the same math problem consistently. Does that make sense? Because when you go to the next one, all you're going to be doing is plugging that 2/3 back in and just doing the same thing over and over again. So that's how that goes. So if you were doing a graph on this, you would do this kind of like this. You would just, use your ends, 1, 2, 3, 4, like that. And then your fraction, I'm just going to go, we have an a sub n axis instead of a y-axis for the terms in the sequence. So you have 1/3, 2/3, and then you have 1 or 3/3 like this. Well, all this is it's just 2/3 always. Okay, so that one would obviously converge, right? Because it's just always going to be the same, like that. So there are times when the sequence just keeps generating a constant, like that. Okay, are you guys following along with the way the recursive thing works okay, and the way the subscripts work? Is that making sense to everybody? Okay, mostly arithmetic at this level, and just kind of getting the idea of how the sequence works then, okay? So let's do one more kind of like this. And this one again is, now this one is an explicit formula. And it's an explicit formula because just one formula there. Okay, so that just gives you everything in one step. So we're going to go ahead and crunch this out. A sub 1, we're going to do 1 minus 10 to the negative 1 and work that out. We're not going to use a calculator on this necessarily. I don't think you need one. So that would be 1 minus 1/10, like that. Okay, make the exponent positive. So that's going to be 10/10 minus 1/10. So that's going to be 9/10. And I'm going to go ahead and just write that as a decimal. So I guess let's just divide by 10, you get 0.9 like that. Now remember, this is an explicit formula, so you just keep number crunching until you see a pattern. You go to A2, you're doing 1 minus 10 to the negative 2, like that. Same idea, that's going to be 1 minus 1 over 10 to the second. So that's 1 minus 1 over 100. Whatever you can do in your head's fine. That's 100 over 100 minus 1 over 100. So that's 99 over 100, okay? And if you take 99 divided by 100, you get 0.99. Okay, and after you do this a couple of times, you'll start predicting what's going to happen on this anyway. What do you predict is the third term in the sequence? Yeah, 0.999, right? Okay, you just keep doing it until you see a pattern. If you don't see a pattern, just keep doing it. So by the same logic, that's going to give 0.99, and then this is going to be 0.9999. Okay, all it does is it just gives you 4 digits of 9 like that. So that's the idea, right? Everybody understand the arithmetic? Okay, no calculus going on here. It's just basic arithmetic and learning how to do the terms of a sequence. Okay, then let's do a graph on this one. And this one is, you just have to estimate this one. I mean, what I'm going to do on this is just do the first 4 terms of the sequence, label that as like an n-axis. And then this would be like the a sub n axis, like that. And where does it look like this thing is going? I mean, is it going to converge or diverge? It's going to converge. It's going to what number? 1, exactly. It's just getting closer to 1. So when I do this, I'm just going to have like a 1 there and maybe a 0.5 there, and you're just going to estimate this. So like that's a 0.9. The next one is just getting closer and closer and closer to 1. So that would be the idea on that, is that's going to converge to 1. Okay, so what we say on this is we would say formally, we would say the limit of the sequence a sub n as n goes to infinity is equal to 1. So we're not to a point where we're doing this analytically yet. We're just graphically getting comfortable with the sequence and visually if it converges or diverges. Okay, does anybody have any questions so far? Okay. All right, this stuff's going to get real interesting. We're only in the beginning. I'm serious. Sequences in series can be really interesting. If you've ever wondered about how do we know all these billions of decimal places in pi, the reason is because we can write pi as a sequence of it can be represented as what we call a series, okay, where we just do some particular formula and it just always gives us the next digit and so forth. So it's kind of similar in regard to this. A formula gives you those particular digits and then supercomputers crunch it out. Okay, so let's talk a little bit about this next thing here. And this one right here, I think I'm just going to do this. Did I put these things on your handout? I don't remember. Sometimes I do, sometimes I don't. So I was just going to show you, I've already shown you how you do technology. This is a really good example of a technology problem. You wouldn't want to do this any other way. So I'm just going to show you kind of what I got on this. And you don't need to put this in your calculator necessarily. So what I did on this one is I put in the sequence, I put in the inverse tangent of 1000 n, like that. And then generally what happens is your calculator sometimes will generate these two things for you. Sometimes you put them in, right? So what I did is I put it in like that. Then my window, I'm going 1 to 10. That way that's just taking the sequence out to the 10th term in the sequence. And then generally this is always the same. That just means n equals 1 is starting at 1, and then it's going up by 1. That plot step is going up 1 each time. And that's typically the default. And then x is going 0 to 10. And then y, I decided to go 0 to 4 like that. So that's how I set that up. Now, if you did this problem, you'd have to be in Radian mode because you're dealing with an inverse trig function like that. So the other thing I did on this is when you get this put in your calculator, you would basically kind of go like this. And I want to go ahead and do this. You can put this in your calculator if you want to. So I'm going to take off what I had here, and I would go inverse tangent. Whoops, not tangent, but I'd have to go inverse tangent. So you got to go second tangent, and then you'd put in the 1000 n. Okay, and see when you type in that variable key, it's since you're in sequence mode, it's going to put it in there for you. Okay, all right. Then if I do the window, I'm going to set that up 0 to 10 or 1 to 10. You can do that. And let's see, I think I did 1 to 10 on that, and then everything else just kind of goes like that, except this goes 0 to 4. And then you want to make sure, if you want to do this with me, you want to make sure that you're in Radian mode. Okay, so let's see, I'm in degree mode, so I'm going to be in Radian mode like that. Put it in, and then we'll get what the graph here is on this. The reason I wanted to put this in, I didn't show you earlier, what you can do if you can tell this thing appears to be converging, right? It appears to be leveling off, but you can also go second graph to get the table to come out, which is kind of nice. There it goes. I thought I had it. Okay. Yeah, so the table will show you what the values are. So what does it appear to be going to? Yesterday was pi day, so you got pi in your mind, right? So it appears to be converging towards pi. If you go out further and further with that, it's just getting closer and closer to pi. That's what it appears to be going to. So a lot of times when we have sequences, and if it's converging to pi, we can use that to figure out decimals in pi. So that's kind of the idea. If you had a supercomputer and kept crunching these decimals out, you would get greater and greater accuracy, wouldn't you? That's the idea. So I'll kind of give you a rough idea of how that works. Okay, so that would be appearing to go to pi, and that would be a problem you'd want to use your technology on at this stage, okay? Okay, all right, let's see. I'm going to do this problem. I always kind of like this problem because this shows you something that you can kind of attach a sequence to. So this is the idea like of a bouncing ball, okay? So what happens is like if you drop a basketball and just let it drop, what's it going to do? It's going to bounce up, not at the same height that it originally did. It's going to just keep going kind of like this, closer and closer and closer to the ground. And eventually it's going to hit the ground. So you can model this by a sequence, okay? So what this problem is saying is that each time the ball bounces off the floor, it rebounds to 0.8 or 80% of its height, okay? And then the initial height is going to be 2,000 feet like that. So we're going to write a formula for this, and then we're going to generate the terms on this. So if you do a recurrence relation, you would write this like this, okay? Now you can start this at h of 1 or h of 0. This time I'm just going to use h of 0. That's kind of your choice on that, really. So I'm going to say what that is that's the initial position of the ball. Okay, that's what's given. It said h naught is 20. Okay, now what your job is on the recurrence relation is to tell me what h of n plus 1 is. So what are you doing to get the next term? The first term, h naught is 20. What do you do to get the next term? According to this, you do 0.8 times 20, right? That's what it tells you. So if you did that on a calculator, if you needed to, that would be 16 feet. Okay, so what you're doing to get that term is you're doing this. You're doing 0.8 times h of n like that. That's the idea. So if you know that if h is 20, 0.8 times 20 gives you the next term and so forth. So that is your recurrence relation. Does that make sense? Okay, you're just doing 0.8 of the previous term. Now let's continue to crunch this out, by the way. So if we go to the next thing, we're going to go 0.8, and then we're going to multiply by 16, okay, the previous term. Some of these things I've already worked out to save a little bit of time. So that's 12.8 feet, if you do that on a calculator. Then you do 0.8 times 12.8. If you get that, that's 10.24 feet. And I'm going to do it one more time. I'm going to do 0.8 times 10.24. So that's going to give 8.192 feet like that. Okay? Is this converging? I hope so, okay, because it's got to come to rest on the floor. So where's it converging to? 0, okay? Eventually it's going to do that, okay? All right? So that's kind of the idea with that. That's your recurrence relation. Now, finding the explicit formula is harder in this problem. So a lot of times what you have to do on this explicit formula is you got to write things out so that you see the pattern that works for every single term. So here's what I'm going to have you do. Let's write down h naught is 20. We know that for a fact. And then we got h1. What we did is we did 0.8 times 20 like that. Now what we want to do when we do this explicit formula, we want to keep that 20 in there. Kind of like that problem I did before. We had 64 everywhere in the problem. You want to relate everything to the beginning. So what happens on h2 is you go like this. And tell me if this makes sense. I'm doing 0.8 of the previous term, but the previous term was 0.8 times 20. Does that make sense? Okay, I didn't crunch out the 0.8 times 20. I want to leave the 20 in there because I want to see the pattern. Okay, let me go to one more term, and then I think hopefully you'll begin to see what's going on. So when I do h3, what am I doing? I'm doing 0.8 times the previous term. The previous term is that whole thing. 0.8 times 0.8 times 20, like that. So if you begin to look at this, there's a nice pattern that exists in here now. So what do you see in your pattern? You always see a 20, right? Now what do you see? A 0.8. Now what is that? 0.8 to the second. What is this? 0.8 to the third. Okay, so if you write it out that way, then you can see that hopefully pretty clearly. So we're now going to write a formula, so it's going to go like this. So if you look at this last term, it's just going to be, okay, that's going to be 0.8 to the third, and then that's just going to be times 20. Okay, this one right here is going to be 0.8 to the second times 20. So when we do the explicit formula, we're going to say h of n to represent height. That's going to be 0.8 to the n power, and then times 20 like that. Okay, that's it. So it's just, and it even works for the first term, because if you did h of 0, you would have 0.8 to the 0 times 20. Isn't that 20? So it works. Okay, so that would be the way that you would figure that out. If you don't write that out, it would be pretty hard to see that. So that is your explicit formula that you have. So the benefit of the explicit formula then is it makes it real easy to answer the question about what the height is at any point in time. So if you wanted to find the height at the 10th bounce, all you do is take this explicit formula and you would do 0.8 to the 10th times 20, and then you could do that on your calculator. Some of this I've already done, so that's 2.147. So you're getting closer to the ground. If you go to the 20th bounce, what are you going to do? 0.8 to the 20th times 20, that gets you to 0.231 like that. Now the mathematics would say that like on the 1/1,000,000th bounce, you still wouldn't be in the floor. Is that realistic? No, of course not, okay? It finally comes to a stop. So the mathematics is modeling this, but we know for a fact that it's eventually going to come to a stop, but it's only modeling this idea, okay? And that's kind of the idea. So what we would say on this, of course, the limit is going to 0. If you did this on a calculator, I just gave you a graph. That's how, if you put the explicit form in the calculator on your sequence, you would get that kind of thing. And that's kind of a picture of what it's looking like that. So that's the idea, okay? So you kind of deal with things like this in physics, with springs and things like this, can be thought of as a sequence, okay? Okay, so is that interesting or boring? That's fairly interesting. You can tie this to different things, okay? That's a pretty good beginning example of something you can use a sequence for. Okay, so I'm going to go ahead next here. I want to work just a little bit on series. And so let's see, on this page, we're going to kind of begin to develop the idea of an infinite series, because that's what we'll be talking about here in a couple weeks after spring break, because that will be our emphasis for a couple weeks is series. We'll be like totally engrossed in that topic. So what I'm going to do today is kind of give you an idea of what this is. So the idea of an infinite series, now it's different than a sequence. A sequence is just a set of numbers that go on forever. An infinite series is you are summing, you are adding things up. So a series would be more like this, 1 plus 2 plus 3 plus 4, on and on and on and on like that. You are adding the terms of the sequence, okay? And what happens on a series is sometimes it will converge to a specific number, sometimes it will not. This one right here obviously would diverge. If you just keep adding bigger and bigger numbers, it just goes to infinity, doesn't it? But if you did this series, like 1/2 plus 1/4 plus 1/8, now remember, the sequence obviously is going to 0, right? So if you go out 1/8, 1/16, 1/32, the infinite term in the sequence is going to 0. But the series is also converging, and it's converging to a specific value. And a lot of times that's a very bizarre idea to a student. How can an infinite sum of numbers become finite? But it can. That's the idea. It just kind of depends on how those numbers work together. So the way you generally do this is you write this sequence like this. You say a sub 1, a sub 2. You just write it in that notation like this. This is a good diagram they have in the book that will show you that this thing, visually, that the sum converges. So here's kind of what's happening. You can think of starting with a square where you have 1 times 1. Okay, that area of that square would be 1, right? So that area is equal to 1. Okay, you can think of it like this. If you kept further subdividing this, this would be like the first term in what we call the partial sum. So that's half of the square right there. Then you do a half plus a fourth. That's what we call a partial sum, because that's the sum of the first 2 terms in the series. Okay, well, that's this part and that part together, right? If you go to the third part and we say S of 3, that notation is saying partial sum of the first 3 terms. So I'm just halving the previous thing like that. I'm cutting the blue shape into half like that. And then I move on. This is the 4th term. And then this is the nth term. So does that help you to visualize? To me, this is great. This helps me visualize that if you just keep cutting the previous thing in half, that thing is still going to be contained in that square, right? Okay? So it turns out that this series is going to converge to 1, okay? Because the area of that square is 1 like that. So if you took this infinite sum of numbers, you'll get 1. Okay, that's pretty bizarre, but that's the way it works out. Does that make any sense? Does that visualization make sense to you? Okay, so a lot of times you can visualize what's happening on an infinite sum. This one certainly is a good example of that. So that infinite sum is going to be equal to 1. Okay, so the next thing I wanted to kind of do on this was this thing can be shown to be equal to this. Okay, so if you add this sum up, I'm not going to go through that, but it can be shown that the value of that sum is that. Okay, that's a formula for that. So if we're going to do the limit of that sum, we get 1. Okay, like that. So that would be kind of the idea. That's just introducing you to the idea of what an infinite series is. Okay, so what's the difference between a sequence and series? What's a sequence? It's a list of numbers, right? 1, 2, 3, 4, 5. What's a series? You're adding the terms of the sequence. Okay, you want to get that in mind. Make sure that you know that. Okay. Okay. So what I want to do next is I want to work on the partial sum idea a little bit, and kind of get that basically established here. So what we're doing on this is a series right here. It's a series because you're adding. There's a pattern to it. You can see what the pattern is. You're just adding another decimal place to that. So when we do a partial sum, that's what this represents. Anytime you see something like that, that means a partial sum of the series, which is real important when you analyze series, okay? Because you're trying to see where is that partial sum going, okay? So when we create this list, we'll get a better idea of whether this is going to converge or not. So the first term in the partial sum is 0.3. So we do that. Second term, we're just doing 0.3 plus 0.03, so that's 0.33. Okay, that just means you added up the first two terms in that series. Then S of 3 is going to mean 0.3 plus 0.03 plus 0.003. So if you do that, you're going to get 0.333 and so forth like that. Now you're beginning to see the pattern, so what's S4 going to be? It's just going to be 4 3s like that. So that's the idea. So what this is not the complete sum. That's only the sum of the first 4 terms. So does this thing look like it's going to go somewhere, or is it diverge or converge? It's going to converge. All it's doing is it's just getting another decimal of 3. And what is infinite 3s in a decimal? What is that number? 1/3, right. So it would appear that if you did this, that if we did the limit of the partial sum, like that, as n goes to infinity, it would appear that that's going to 1/3. Okay, like that. So that would be another example of a sum that's adding to something. So really what this means is it really means 3/10, that's what 0.3 is, plus 3/100, plus 3,000ths, and so forth. What that's going to do is eventually you're going to get to 1/3 if you add that infinite number of fractions up. That's the idea. Okay? Pretty bizarre idea, but it works. Okay? All right. Does that make sense what I'm talking about with partial sums to everybody? Okay? All right. Let's do one with this real quick so kind of get some sort of an idea of what's going on this. The first term's 1. Okay? You want to get the second term in the partial sum, you're just going to do 1 plus 1/2. Okay, I'll do this arithmetic real quick. So that's going to be 3/2, like that. Okay, the third term, you're just doing 1 plus 1/2 plus 1/4, like that. Or you can do it like this, or you can just add up the previous term like that. So that's really 4/4 plus, and then that would be 8. What am I doing? Nope. 2/4, sorry. So 4/4 plus 2/4 plus 1/4 would be 7/4. And you would just keep doing that forever and getting that. Now, I'm not going to do the next one. It's just the idea with this one is you'd have 1/1 plus 1/2 plus 1/4 plus 1/8. If you work that out, you'll get 15 over 8. I'm not going to show the details on that because that's basic arithmetic. Okay, so does everybody understand the idea of a partial sum okay? All right. Now, the idea with this is does this thing look like it's going anywhere, or does it look like it's just going to just go to infinity and diverge? What do you think? You got let's see, 3 over 2, 7 over 4, 15 over 8. What's the relationship between the numerator and denominator? What does it look like it's getting close to? 2, exactly. It looks like 15 is almost double 8, so it looks like they're just getting close to that number 2. So it would appear that that's going to 2. That doesn't prove anything. That's just, okay, it appears to be, that would be our conjecture. Then we would have to analyze and prove that then like that. So that would be the idea of the partial sum like that. Okay, any questions about what a series means and what a partial sum means? You got to get that really, really clear in your mind before we continue going through this. So let's go ahead and do our break right now. Once you come back at 15. So let's see, to begin with, just a little bit of notation that we've really already talked about. So again, if you have a sequence, when you're doing a sum of its terms, that's when you're making a series. Now, depending on your background, you may not have seen this type of notation very often. You see that a lot in statistics and somewhat in some other areas as well. It's a big thing in statistics. But what this stands for, that's the Greek letter sigma. We usually just call that a sigma sum. And what it's saying is, that is telling you that you're summing the members of the sequence. So a sub k is some sort of a sequence, and you're summing its terms, and you're going from k equals 1 to infinity. So k is 1, k is 2, 3, whole numbers, and forever, like that. That's what that notation means. And then S of n is a partial sum, like I talked about in the previous example. And all that means is when you're analyzing the convergence or divergence of an infinite series, you want to look at a sequence of partial sums and see if that's going somewhere. So again, the first term is just the first term, then you add the first 2 terms, add the first 3 terms, and so forth, and that gives you a sequence of sums. So the idea is kind of like that last problem I did. When we got to the 4th sum, we were already beginning to see that this thing is converging. So generally what happens is if you just analyze maybe the first 5 or 6 terms of a partial sum in a series, you can oftentimes begin to see whether it's going to converge or not. Not always, but a lot of times that's the case. Okay, so what I want to do with this is, and we kind of talked about what it means to converge. The idea is if you do the limit of this of the partial sums, if that's equal to L, then we're going to say that's converging. Like on the last one, if we did the limit of this partial sum, as n goes to infinity, that would be going to 2. That's what it appears to be doing. Otherwise, it diverges. So that's just kind of the terminology. Okay, we'll get a little bit more formal on this one now. So this one is an infinite series. That's the type of notation you're going to see and get comfortable with. So we're going to go ahead and write the partial sums out. So the first thing I want to do on this is let's go ahead and let's just write out the first several terms on this. So you want to be able to write the terms of a series out. So you're going to have 1 over 2 to the first, plus 1 over 2 to the second, plus 1 over 2 to the third, and then so forth forever and ever and ever. And then eventually you just have 1 over 2 to the k like that. So all you're doing is 1 over whole number powers of 2. That's it. So we're going to write out the sequence of partial sums. We're not going to write out the members of the sequence. We're going to write partial sums. So the first thing is just the 1/2. Okay, the second thing is going to be to take 1/2 plus 1 over 2 to the second. So that is 1/2 plus 1/4. And if you work that out, that's 2/4 plus 1/4, so that's equal to 3/4. Like that. Okay, we're just going to keep adding these members of the sequence up. Now, a lot of this arithmetic I'm not going to do. I'm just, because I've already done some of that, I don't want to spend a lot of time on arithmetic. So the next one, you're doing 1/2 plus 1/4 plus 1/8. Those are adding the first 3 members of the sequence. If you do that, you get 7/8. Okay? All right? And you can do this kind of stuff too with your calculator. I mean, if you get in a crunch, you can add fractions with your calculator and do that if you want to. If you don't remember that, I'm going to just show you real quick to remind you, because that comes in very handy sometimes if you got a bunch of fractions you're adding. So if you do like 1/2 like this plus 1/4 and then plus 1/8 like this, it'll just give you a decimal is all that's going to give. But then you have the ability to convert it to a fraction if you go press your math button, and then option 1 is convert to fraction, so it'll do that for you. So that comes in real handy. If you don't know how to do that or haven't done that in a long time, make a note of that, because you will need to do that from time to time. Okay. The next one, what we're going to do, again, you can do this either by hand or arithmetic. You're just doing 1/2 plus 1/4 plus 1/8 plus 1/16. So that's going to give 15/16. Okay, so if you look at this particular problem, see, this is the sum of the first 4 terms of the series. Does it look like that's going to level off at a certain number? Is it going anywhere, in other words? Yeah, it looks like it's going to 1. Okay, it pretty well looks like that's going to be the case. Now, we're going to do this one a little bit more formally. So we're going to find a formula for S of n. Okay, and what I'm going to do on this is kind of look at this sort of like this. So let's write down a good way to do this is write down these first 4 numbers. And remember, this represents sums. We have a sequence of partial sums. And let's see what we have, okay? What's the pattern that you see in the denominator? 2, 4, 8, 16. Those are powers of 2, right? Okay, you got powers of 2. So if you do that, you're going to have 2 to the first, 2 to the second, 2 to the third, 2 to the fourth. Okay, so we have that. Now that's pretty easy to see. The numerator, I want to see if you see the numerator on this. There is a pattern on that numerator. I want to see if you see that. What'd you say? Good, that's right. Okay. Isn't the numerator always 1 smaller than the denominator? Okay, so if you did this, see the next term, you would predict that the next term would be 32 and then 31, right? And then after that, you would have like 64 and 63. That's how it goes. So exactly, this thing is going to be 1 less than the denominator. Okay, so that would just be 16 minus 1, 8 minus 1, and so forth like that. Okay, so that means that the formula would go like this. You're going to have a power of 2, so we'd say 2 to the n, and then the numerator is the same thing, but it's less 1 like that. So that's what S of n is. That's an explicit formula for the partial sum. Okay, and it's all about pattern recognition. I recommend you just write things out, see whatever patterns you see. Sometimes it's easy, sometimes it isn't. Okay, so now what we're going to do is we're going to do the limit of the partial sum, and we're going to do this formally. We're going to do the limit as n goes to infinity. So that's going to be represented by the limit as n goes to infinity of this explicit formula, 2 to the n minus 1 over 2 to the n like that. Now we're going to kind of finally get into the calculus we know, and we're just going to focus on that limit. Okay, there's several ways to do this. One way to do this is, if you look at this, you have like 2 to the infinity minus 1 over 2 to the infinity. Okay, that numerator is infinite, and so is that denominator. Okay, that's what we call an infinity over infinity in indeterminate form. Do you guys remember anything about L'Hopital's rule? Yeah, we're going to do that a lot. I'm not going to do it on this problem, but we're going to be doing this a lot as we continue working with series. I'm going to do this way. Okay, one way to do this is like this. You can split this up. So we're going to break this up into 2 to the n over 2 to the n minus 1 over 2 to the n. That's probably the simplest way to do this. L'Hopital's rule, you'd have to differentiate 2 to the n, which is not a hard thing to do, but it's a formula a lot of times that students don't remember very well. So I just do this. So what I really have is I have the limit, that becomes 1 as n goes to infinity, minus the limit of 1 over 2 to the n as n goes to infinity like that. Now we got everything we need to know. What's the limit of a constant always? Just itself, so that's 1. What's the limit of 1 over 2 to the n? That's really 1 over infinity, so where's that going? To 0, right? If you do 1 divided by a bigger and bigger number, that goes to 0, so you're going to end up having 1 like that. So that's more formally how you would figure out that that sequence of partial sums is going to 1. Okay, that's applying limit stuff that you did in Calc 1. Does that make sense? Okay. Hopital's rule works on that, but it's to me, it's just as easy to do that one that way then. So we're going to do a couple of more of these, just one more of these things to get kind of comfortable with this. Is there any question about what I did there? The key thing is listing the partial sums, just sort of looking in your mind whether it appears to converge, finding an explicit formula and doing the limit. That's what we're trying to do with this then. Okay, so this one, we've got a different infinite series. So let's go ahead and let's write out the terms and just kind of get that put together. So the first term we would have is 1 over 4 times 1 to the second minus 1. And it's a series, so we're going to keep adding the terms. Then it would be 1 over 4 times 2 to the second minus 1. 1 over 4 times 3 to the second minus 1. And so forth. I'm just going to write out about 4 terms. And then this stuff, a lot of this stuff you'll be able to do in your head okay. All right, so you're just going through and plugging in 1, 2, 3, 4, and so forth like that. Okay? Now just go through and let's do this in our head and see what these are. Okay, this is 1 over, that's 4 minus 1, so that's a third. This is 1 over, this is 4 times 4 is 16, minus 1 is 15. Okay, then this one is 9 times 4, 36, minus 1 is 35. The last one, that would be 16 times 4 is 64, minus 1 is 63. So that's what your infinite series is. Those are your general terms like that. Okay? Now what we're going to do is, our goal is to analyze if you added up those infinite number of fractions, do they go anywhere or do they just go to infinity? Okay, that's the idea. Okay? All right, everybody okay so far? I'm doing arithmetic. Okay, that's the easy part. Now I'm going to do the partial sums. What is S1? 1/3, whatever I start with. Okay? Now all these things I'm not going to do all the fraction arithmetic. I'll do one of them. So like, now we're going to do 1/3 plus 1/15. So you would get a common denominator, you know, multiplying that by 3 over 3 to get 3 over 3. See, look, I can't do any of the easy stuff. Gosh, man, I'm ready for spring break. Okay, how about multiplying by 5 over 5? Okay. All right, so let's see. That's going to give 5/15 plus 1/15. Okay, so that is 6/15. And then that reduces to 2/5, like that. Now that's the only one I'm going to do. Again, when you're doing like homework and stuff on that, you know, I want you obviously to know how to add your fractions, but you can use your technology to speed yourself up a little bit on this too. So S3 is just 1/3 plus 1/15 plus 1 over 35. I'm just going to tell you the answer. It's 3/7. Then we're going to do 1/3 plus 1/15 plus 1 over 35 plus 1 over 63. And I'll tell you that's going to be 4 over 9. Okay? Because the key thing for you is to get those partial sums written out enough terms so that you can begin to see a pattern. Okay? Everybody with me of what I'm doing there and what I mean by a partial sum. Okay? Now, just look at this. Does this look like it may be going somewhere? 4 over 9, do you think it's going anywhere? Or is it just going to be going to infinity? What do you think? It's getting close to something. What is it? Probably a half. Probably. Okay, that would be my conjecture. Okay, we're getting close to a half. Okay? All right, so let's kind of analyze this a little bit more formally. So we're going to find a formula for the partial sum. So let's do that. Okay, we have 1/3, we have 2/5, 3/7, and 4/9. That is a sequence of the partial sums of the series. Okay, so let's see what we got on this now. Let's see what kind of pattern we got. What do you notice in the denominator? Those are odd numbers, right? Okay, those are odd numbers starting with 3. So you have odd numbers there. Okay, how about the numerator? Those are just whole numbers, right? Okay, those are whole numbers. So whole numbers going up by 1 like that. So basically what you have, now one thing that I think is probably a good thing for you guys to write down is anytime you have an even number, you can write an even number mathematically as 2n. Okay? Remember, n is a whole number. So if you double any number, don't you get an even? 2 times 3 is 6, right? 2 times 11 is 22. Anytime you double any whole number, you're going to get an even number. Well, here's an odd, and an odd is very logical. How do you get an odd number? You take an even number and add 1 to it, and you always get an odd, right? So that's a good thing to write down because you utilize that a lot. Even numbers are represented with 2n, and then odd, you can also do an odd as 2n minus 1. It doesn't make any difference. Okay, still you're going to get an odd number out of that. Okay, so if you do your general formula now, it's going to go like this. Well, the numerator is just going to be n, because that's what n is. N is a whole number. It's going to go 1, 2, 3, 4, and so forth like that. Okay, now what this is going to be is an odd number. So let's do 2n plus 1, and let's just make sure it works. Okay, anytime you get a formula, make sure it's right. So basically what's happening in this problem is if n is equal to 1, what do you have? You have 1 over 2 times 1 plus 1. That's a third, isn't it? Okay, and it'll keep working. You go to n equals 2. Now you've got 2 over 2 times 2 plus 1. So that's 2/5 and so forth, like that. Okay, so that's the idea. Does that make sense to everybody what that formula is and how I came up with it? So this is probably real important to know. It's easy to remember that, and you're going to express that like that then. So now what we're going to do is we're now going to do the limit, and we're going to do this like this. We're doing the limit as n goes to infinity of the partial sums. It appears that it's going to a half, but we're going to be a little bit more formal than when we do this then. Okay, so as I do this, we're now going to be looking at the limit as n goes to infinity of n over 2n plus 1. Okay, now this depends a lot on what you remember from Calc 1. There are several ways you can do this limit. Okay, one way is to do this approach. Okay, some of you may remember enough that you could tell me, boom, boom, what it is. I can tell what the value of that limit is. If you can't, I'll show you here in just a minute. So let's do it this way because you want to know different strategies. One thing that you usually learn in Calc 1 is if you have a rational expression, if you divide by the highest power of your variable, that turns out to be something that's very beneficial. So I'm going to do it that way first of all. And then we'll talk about a couple other techniques that you could do to get the same thing. Okay, so what I would have is I'd have the limit as n goes to infinity of 1, n over n's 1, 2n over n would be 2, plus 1 over n like that. Okay, that's how you could do that. All right, now if you think about this, all that's happening on this is you have 1 over 2 plus 1 over something infinitely big. What is 1 over infinity? What's that becoming? 0, right? Okay, so what you end up having is you have 1 over 2 plus 0, so it's equal to a half. Okay, that's one way to look at the problem. Does that look familiar? Okay, dividing by the highest power. That's one way. Now, here's another way. And this is worth noting. Okay, if you have a rational function, it usually has, or not always, but sometimes it has a horizontal asymptote. Okay, for instance, if you had something like this, x squared over 2x squared plus 2. The degrees are the same, so you may remember learning that if the degree of top and bottom are the same, then there's your horizontal asymptote. And that's what a horizontal asymptote is. It tells you how the graph behaves as you go to infinity. Do you guys remember anything about that? That's what I was saying. I already knew it was 1/2 just by looking at it, which is okay. I would want you to be able to do that. Another approach would be L'Hopital's rule. So if you had, going back to this same limit again, okay, first thing you would have to realize that that's an infinity over infinity limit. Okay, now you just do this. By L'Hopital's rule, what did you do in L'Hopital's rule anyway? You do the derivative top and bottom. What's the derivative of n? 1. What's the derivative of n plus, 2n plus 1. What's the derivative of 2n plus 1? Okay, see what I mean? Okay, and then you know the limit of a constant's 1/2. So you have those different approaches. One thing about L'Hopital's rule, you don't want to just jump in and do it. You have to verify that it's a 0 over 0 limit or an infinity over infinity limit. Then you can go proceed that way. Okay, now we're going to talk a lot more about L'Hopital's rule in the next section. Okay, so that would be 1/2. That would be our conclusion. Okay, and that's doing that a little bit more formally. Okay, any questions on that? Okay, all right, let's look at this one. So let's see, when I do this one right here, let's see, what does that -1 to the k tell you in this series? What's it doing? It's alternating, right, that's important, okay? So let's go ahead and let's write out the terms, kind of get this one going here. So we would have -1 to the first would be the first term in the sequence, plus -1 to the second, plus -1 to the third, plus -1 to the fourth, and so forth, right? Okay, so what's going to happen on this is it's going to alternate, because anytime you have an odd exponent, that's going to be -1, right? Anytime you have an even exponent, that's going to be +1. So the sequence is, the series is going to go like this: -1 plus 1, plus -1, plus 1, and so forth forever and ever and ever. Okay, oh, hold on, I'm forgetting one part of this. I'm not paying attention here. I need to be careful about that. That's how that goes, but what did I forget? I forgot all about that guy. Okay, all right. So let's slide that thing in there then, okay? So that's just going to be times 1, times 2, sorry about that, times 3, times 4, and so forth like that. So I was so into the alternating part of that, I forgot about the k. So what you would have then is you would have this. You would have -1 plus 2 minus 3, and then plus 4 like that. Okay, because you're just multiplying that power of -1 by whatever k is. Okay, everybody understand that okay, and how that's working? Okay, all right, well, what's S1? -1, okay. S2, you're going to do -1 plus 2, so that's 1. No fractions this time. S3 is -1 plus 2 minus 3, so what's that? -2, I think. Okay, then you got -1 plus 2 minus 3 plus 4. You work that out, that's plus 2 like that. Okay, so again, now that we've written out the first terms of the series, the partial sums, does this look like it's going anywhere? What do you predict comes next? -3, 3, -4, 4, -5, 5. That's what it appears to be, so it appears to diverge. Okay, and sometimes that's going to happen on that. So the idea would be, if you put this together, if you did the limit as n goes to infinity of this expression, that would diverge. Okay, it's not going to go anywhere. Okay, so that would be kind of the idea with that. Then you can tell that pretty much by just looking at how that partial sum goes. Okay, is there any questions about that? Okay, what do you guys think of sequences? I think they're cool. I do, I really do. There's some interesting math problems out there in